Every time you load a web page or stream a video, your data isn't floating through the air. It's racing through a glass thread the size of a garden hose, resting on the silent, crushing floor of the Atlantic Ocean. These cables are the literal nervous system of our planet, spanning hundreds of thousands of miles across the abyss. But at depths of 3,000 meters, the environment is so hostile that even the simplest mechanical task becomes a masterclass in engineering. Finding a 2-inch wide cable in the vast, pitch-black expanse of the ocean floor is like trying to find a specific needle in a haystack while wearing oven mitts and standing on a moving boat. This is where the Cable Snatcher comes in. The pressure at these depths is staggering, over 300 times what we feel at sea level. Any tool sent down there has to be built to survive forces that would crush a standard car like a soda can. Engineers solve this by using pressure-compensated systems, where the internal components are bathed in oil that pushes back against the ocean. It's a delicate balance of physics that allows complex machinery to function in the dark. But survival is only half the battle. The real magic happens when the machine actually makes contact with its target, using sensors that can feel the difference between a rock and a billion-dollar data link. Imagine trying to identify an object you can't see, using only sound. That is the reality for subsea operators. The seabed is littered with debris, shipwrecks, and jagged rocks that look exactly like cables on traditional sonar. To solve this, engineers developed acoustic signature sensors. These devices emit specific frequencies and listen for the unique thrum of a hollow, layered cable compared to the solid, dense echo of a rock. It's a brilliant application of material science. Because the cable is made of distinct layers, steel, copper, and glass, it reflects sound in a way that nothing else on the ocean floor can mimic. Once the cable is identified, the Snatcher tool must move in. This isn't just a simple hook. It's a multi-stage hydraulic system designed to secure the cable without crushing the delicate glass fibers inside. The claw uses pressure-sensitive hydraulic valves. Think of it like a robotic hand that can grip a grape without breaking the skin, but has the power to lift a school bus if needed. This variable force is critical. If the grip is too loose, the cable slips away in the current. If it's too tight, you've just caused a multi-million-dollar internet outage before you've even started the repair. But what happens when the cable needs to be cut? Whether for decommissioning or emergency repair, engineers have designed shearing tools that make a hot knife through butter look like a struggle. The engineering behind these blades is a story of extreme materials and clever geometry. We're about to dive into how they slice through layers of armored steel at the bottom of the world. From the physics of the touch to the brutal efficiency of the cut, the Cable Snatcher is one of the most specialized tools ever built. And the deeper we go, the more impressive the engineering becomes. To understand how a machine sees at 3 kilometers deep, we have to look at acoustic signature sensors. These aren't just microphones, they are high-frequency transducers that map the internal density of objects. When the sensor pings a rock, the sound wave returns as a chaotic, high-amplitude mess. But when it hits a fiber-optic cable, the hollow copper core and the specific winding of the steel armor create a predictable, rhythmic echo. This allows the ROV's computer to filter out the noise of the seabed and lock onto the cable with surgical precision, even when it's buried under a meter of silt. Once the cable is located, the hydraulic claws take over. These are controlled by force feedback systems. As the claw closes, sensors measure the resistance and adjust the hydraulic flow in milliseconds. Think of it like a high-tech version of your own hand. You know exactly how hard to squeeze a paper cup so it doesn't fall, but also doesn't collapse. The Snatcher does this with thousands of pounds of pressure. This sensitivity is achieved using piezoelectric crystals that generate a tiny electric charge when compressed. The more the cable resists, the higher the voltage, telling the system to stop squeezing. But sometimes the goal isn't to hold, it's to destroy. When a cable is damaged beyond repair, it must be cut. This requires shearing blades that can generate over 50 tons of force in a single stroke. The secret is in the bypass shear design. Instead of the blades meeting edge to edge like a wire cutter, they slide past each other like giant scissors. This prevents the cable from flattening and increases the cutting efficiency. This geometry ensures that the force is concentrated on a tiny point, allowing the tool to slice through the high-tensile steel armoring that protects the cable's core. The blades themselves are a marvel of metallurgy. They're typically made from a specialized tungsten carbide or a nickel-chrome molybdenum alloy, designed to stay sharp even after multiple cuts through abrasive steel. At these steps, standard steel would become brittle or corrode instantly. These alloys are engineered to resist the hydrogen embrittlement caused by the high-pressure saltwater environment. Every cut is a violent event. The energy released when a high-tension cable snaps can vibrate through the entire ROV, requiring the snatcher to be mounted on heavy-duty shock absorbers. To power these massive shears, the ROV uses a hydraulic intensifier. It takes the standard hydraulic pressure from the ROV's main pump and steps it up, like an electrical transformer, but for fluid. This allows a relatively small robot to generate the brute force of a factory floor press. It's the ultimate combination of finesse and power, hidden in the darkest corners of our world. But as these tools got better, the cables themselves started to fight back. Engineers began designing cables that are specifically built to be uncuttable. Modern submarine cables are no longer just wires, they are armored fortresses. To resist the shearing tools we just looked at, engineers have developed hardened cable architectures. The first line of defense is a layer of galvanized steel wires, often wound in opposite directions. This counter-helical winding prevents the cable from twisting and makes it incredibly difficult for a blade to find a purchase. If you try to cut it, the wires don't just snap, they shift and slide, absorbing the energy of the shear and spreading the force across a larger area. Beyond the steel, some cables use a layer of beryllium copper. This alloy is nearly as strong as steel but has a unique property. It doesn't spark and is incredibly resistant to the fatigue caused by repetitive mechanical stress. This makes the cable's core almost immune to the high-frequency vibrations used by some cutting tools to weaken the material before the final shear. It's a literal arms race. For every new hydraulic shear developed, cable engineers add a new layer of high-performance polymer or metallic alloy to stop it. At 3,000 meters, the cold is also a factor. The water is near freezing, which can make many materials brittle. To counter this, cable jackets are made from high-density polyethylene that remains flexible in extreme cold. But the most impressive part is the water-blocking gel. If the outer layers are breached, this specialized petroleum-based compound instantly swells up, creating a waterproof plug that prevents the entire cable from flooding. It's a multi-layered system of defense that makes these cables some of the most resilient structures ever built by human hands. When a repair is finally made, the snatcher tools are used in reverse. The ROV must carefully align the two ends of the cut cable, each weighing thousands of pounds, with millimeter precision. They use laser-guided docking systems to ensure the fibers are perfectly aligned before they are fused back together using an electric arc. It's like performing heart surgery in the middle of a hurricane. This cycle of cutting, hardening, and repairing is what keeps our global internet running. It's a hidden world of mechanical brilliance that happens every day, miles beneath the waves. Next time you send a message across the world, remember the cable snatchers. Remember the hydraulic claws that can feel a single wire and the shearing blades that can slice through armor at the bottom of the sea. The engineering required to maintain our digital world is just as impressive as the data itself. It's a testament to human ingenuity, solving the impossible 1 kilometer at a time. In the dark, crushing depths of the abyss, the most advanced machines we've ever built are working silently to keep us all connected. And that is truly a wonder of the modern age.